Speaker is Artem Sobolev, who will give a talk about his recent research, which was submitted to ICML and received quite good reviews. In some sense, we continue it as a further development of Semi-Implicit Variational Inference, which has been developed in our group for a while. And the topic of today's talk is importance value of hierarchical variational. Yes, importance value of hierarchical variational inference. Please.
Hello everyone. So the topic of my talk has been already declared. So without further ado, let us start. But first I probably should caution you that this will be a math-heavy talk. Well, this is variational inference. It's not that easy to give fancy pictures here. Instead, it is easy to give fancy formulas. Luckily, you won't need any special math. This is not some Riemannian optimization talk where you need to quickly get familiar with this new notation. We'll be just using the usual properties of expectations, logarithms, summation, products, and so on. Okay, let me first remind you what variational inference is, what it's all about. So imagine you have some observations axis, and you want to build a model of this axis, of this observable axis that you have. However, you think that axes have a very complicated dependence structure in it. Maybe those are images, and you observe raw pixels. It's very hard to tell how the raw pixels actually depend on each other. So what you instead do is you assume that there is a latent variable model that describes your data well, that there is some unobserved z, that if you knew z, then it would be much easier to describe the dependence in axis. So you assume that the data is generated by the following process, where you first decide on some global characteristics of your datum, the z, and then based on that z you generate the x with probably much fewer dependents in it. Now, of course, the problem is that we don't know these z's, and integrating this expectation analytically is intractable, so we don't have the access to marginal density anymore, and we would like to do maximum likelihood estimation, which requires us to know this quantity. So instead, we go for a lower bound, we introduce variational distribution Q, and write down essentially this such a lower bound. It's called the evidence lower bound, short for elbow. And as the name suggests, it's always a lower bound. Yeah, so let's see how good it is. We know that the gap between the marginal log likelihood, the log p of theta, and the elbow can be is actually equal to Kyle divergence between our proposal Q and the true posterior of your model P of z given x. By rearranging the terms, we can see that well, actually the elbow is just the marginal likelihood that is offset by this Kyle divergence. So what does this thing mean? Well, first, if you optimize your elbow with respect to phi, your variation distribution parameters of the variation distribution, then it does very sensible thing. It approaches the true posterior, and this way you can also find the true posterior if you are Bayesian and care about such things. But what would happen when we optimize over theta, over parameters of our distribution? This is actually the thing we probably care about the most, since in this case, in this formulation, we are doing maximum likelihood learning, and we actually don't care that much about the Q, the variational distribution, but we care about the learning, finding good thetas. So when we optimize over theta, we not only maximize the... So look at this formula. It clearly shows us that when you maximize elbow with respect to theta, you not only maximize the marginal likelihood, but you also have this regularizing term that says that you should not allow your posterior go far away, your true posterior go far away from the approximate one, from the variational distribution. So when you optimize by over theta's, you not only increase the marginal likelihood, but you also move your posterior closer to the approximate one, towards the cube. And this is actually not a good thing, because, well, it can be argued whether this is a good thing, but if you want to have an expressive marginal distribution, P of x, of marginal x, then you don't really want any constraints on your true posterior. You don't care about your true posterior, whether it's simple or not. But such a regularizer sort of forces this upon you. So in practice, we would like to have more expressive variational distributions. And this is, I guess, the main topic of the field called Approximate Inference, which Variational Inference is part of. So what can we do about this variational expressivity? Well, as I said, this variational distribution acts as a regularizer. So in VAEs, for example, I guess the well-known model to all of you, variational distribution is just a Gaussian distribution, and even though there are neural networks involved, they do not increase the expressivity of this distribution. They are only used to amortize the inference, so that we don't need expensive computations to find parameters of this distribution. You could spend more computation and compute full Gaussian distribution instead of factorized one, but it will still be Gaussian, not very expressive distribution. So the other direction of great interest here is to leverage universal approximation capabilities of your neural networks to approximate arbitrary distributions. For example, a neural sampler, what I would call a neural sampler, works this way. You sample some standard, from some simple distribution like standard Gaussian, 2D Gaussian. Then you pass this sample through some neural network that you learn somehow, and then the output sample is distributed according to some different, much more complicated distribution. Now, this is a very neat use case of neural networks, using them as neural samplers. So can we use them in our case? So let's see, here we have our elbow, and there are two places our variational distribution comes in. First, we need to sample from this distribution, and then we need to compute actually the elbow. The sampling is easy. If you want to sample from the neural sampler, you just sample this input noise, run it through a neural network, and there you go, here's your sample. But this term is much more troubling. It requires us to know marginal density of our samples that are output of the neural network, and it's not easy to compute in general. But it's not the first day people thought about such problem. There's been a lot of work on this topic. I would roughly categorize them in three different categories. First is invertible, well, the so-called normalizing flows, invertible transformations where you can efficiently compute the Jacobian, and thus you can actually efficiently compute this density. While they are very theoretically sound and practically appealing, there have been some works that show that they do work somewhat well. I think that I have this feeling that they require this invertibility requirement leads to sort of huge parameter complexity. They need a lot of parameters to learn these invertible maps, whereas maybe we can, if we if we don't care about invertibility, then maybe we can go and do it with fewer parameters and train more lightweight models. So another direction.
And what about country abstraction? What do you mean?
Sorry, what abstraction?
It's written that normalized poles.
Oh yeah. So the problem here is that in order to have invertibility, you need the input to be of the same size as the output. So this is what I call by abstraction. You can't generate some high-dimensional structure out of the low-dimensional one.
Mm-hmm.
So this is sort of, they can't invert abstraction, I would say.
How we can compute conditional probability for continuous for normalized pole? Here we have QZ given X.
Well, you parameterize the whole conditional distribution using sort of conditional flow. For example, in the flow, you have some neural networks that take your epsilon.
Yes.
So, like on this picture, you have this network. Assume that this is a network that implements a normalizing flow. Then you can sort of concatenate the input noise with the x that you would like to condition, and also pass it through. And you don't actually need to care about invertibility with respect to that x. So in the design of your normalizing flow, you can find these spots, these like convolutional layers or fully connected layers that you can condition on the x. So it's not that hard to actually inject some extra knowledge into these parameters of the normalizing flow. Or maybe you can just generate this simple distribution by a standard encoder from the VAE that takes x and outputs your mean and the standard deviation, and then run this sample through unconditional flow. So another direction to deal with such models with neurosamplers is to use some approximate models that would approximate the ratio of two densities here. So the most famous example is probably the density ratio trick, and this approach is closely related to GANs, generative adversarial networks. The problem here is that when you go for such approximations, you usually lose the bound guarantees. So what you end up with is not a lower bound on the marginal likelihood anymore, and it might be troubling, or at least not so elegant from the mathematical point of view. Finally, there is the third option that we will go for, and that is, okay, so if we can't compute this density exactly, so can we come up with a bound with it's obviously a lower bound on the elbow, so that would be tractable, and probably, then if we come up with a bound, then another question arises of how tight this bound is. If it's not very tight, then it's not very useful. But this is the topic we will be exploring in much greater detail. So what will be interested in is the so-called hierarchical proposals, where basically you have another VAE as your proposal. You say that the marginal distribution of the condition of x is obtained by marginalizing some joint over the auxiliary variable psi. The only thing we assume from these two distributions is that they are easy to sample from, and they can be reparameterized, so that we can learn the whole thing by reparameterization trick. Although the reparameterizability is not such a hard requirement, I guess one could go for a reinforced estimator if they are comfortable with it. But now, so again, we have we committed to go for a lower bounds. So if we want to get rid of this intractable log density of the proposal term, we need to bound the elbow from below to preserve our guarantees. Or equivalently, we need to find an upper bound on the marginal log density of Q. Some of you might think that, wait, I heard about some bounds on marginal log likelihood. We use just that to derive the elbow. Can't we use the same here? Well, the problem is that the standard variational bound gives you a lower bound. And if you plug this in, you would have an upper bound on elbow, which is not guaranteed to be either lower or upper bound on the marginal log likelihood. So you can just use the standard variational bound here. However, actually there is a simple variational bound that you could use here. And it stems from the following, it looks like this. Let me show you why this is indeed a lower bound. It follows from the simple fact that if you, so consider this random variable that you expect over distribution Q of psi given z and x. Then it is easy to see that its expectation, it is unbiased estimator of 1 over marginal distribution of z. Why is that? Well, because essentially what this thing is, if you consider it as an integral, then the posterior distribution, the inverse models on psi would cancel out. You will have only the marginal in the denominator. And, the denominator will be independent of psi, so you will only need to integrate tau, which integrates to 1. Now that we know that this is an unbiased estimator of this quantity, we can apply the logarithm and use its concavity in conjunction with the Jensen's inequality to obtain the following bound. So now that this essentially shows us that in this formula we can move out the joint density of x and z out of this expectation, and this expectation will be bounded from above by the logarithm of 1 over q. So combining the all terms together, we'll get back our elbow, and this finishes the proof. One can also negate both sides of this identity and obtain variational upper bound on marginal log likelihood, on marginal log density of the following form. Compare it with the standard variational lower bound of the following form, of this form, and the only difference, as you can see, comes from, in fact, which distribution we use to sample our psi's from. We sample psi from the true posterior, then we get an upper bound. If we sample psi from the variational distribution, we get a lower bound. Well, that's a neat result. However, sampling from the true posterior is complicated. In general, you would need some Markov chain Monte Carlo, and this is not something variational people like.
Before we proceed, what would be the gap between the upper bound and the log of marginal?
We will discuss it later.
Okay.
For now, the question is, how do we do with the need for samples from the true posterior? And here we use the fact that we're not interested in samples from the true posterior for arbitrary z, but only actually for z's that come from our distribution. And we know how, and in order to sample from our distribution, we actually first generate psi, and then by running psi through a neural network, we have our z's. So by joining these two distributions into the join, we can leverage the fact that we can factorize it in an arbitrary way. For example, we can factorize it like this, and then in the same, you get the same thing under the integral as our estimate. So, in a sense, if you sample your z and psi as following, first you sample psi and then sample z from that psi, then you can sort of think of that psi as coming from as one sample from the true posterior for the given z. That removes the need for the Markov chain Monte Carlo. So this has not been known, and it results in the following lower bound on the marginal likelihood, where tau of eta is auxiliary variational distribution, and Q is our standard, is our joint variational distribution. So we derived it from the assumption that Q is also a hierarchical model, but one can take a look at this formula and arrive at a different interpretation. You can say that the term in the denominator, this product of the joint density and the tau, the auxiliary variational density, it can be, one can say that this is actually an extended density, an extended joint density of your model. And Q of z is not the joint proposal density, but the whole proposal. And now you're doing variational inference in the space not only of z, but in the extended space of z and psi. So,
but we also optimize with respect to eta, with respect to tau, right? So this is not just extended space.
This is kind of a variational, kind of an empirical bias.
I would not call it empirical bias.
Well, okay, so here if we forget about the inference and learning separation and only think about, only consider the whole thing as a lower bound of the marginal density.
Right. So we have two groups of variational parameters, phi and eta.
Well, okay, right. So in this formulation, optimizing over eta does not lead to increase in marginal likelihood, but only tightens your bound. So that, in that sense, it is not exactly equivalent to considering an extended model, but this is actually so, it is designed to be so. Because if optimizing over eta would affect our marginal log likelihood, then that would interfere with our assumed model. In this case, we assume that our generative model that we actually care about is very simple. Is the one where you first sample z and then sample x given z. And psi does not exist in this model at all. So we would actually, if you were to come up with this thing from scratch, you would actually want to design it in such a way that it is joint distribution over z, psi, and x, but you don't want the sampling pipeline to be messed up. So yeah, this method is known as the auxiliary variables method, and also as hierarchical variational models, which is roughly two different views on the same bound.
If such low bound more tighter than just usual L bound?
We're about to discuss it. So, but first notice that, so here we traded lower bound, we traded elbow for a lower bound on elbow. And the gap between the elbow and our new lower bound, the sort of double lower bound, can be expressed as another Kyle divergence. So now, when you optimize over eta, nothing fancy happens. You only approximate this true inverse model of your proposal Q. But when you optimize over phi, you not only approximate the true posterior of your model P, but also have this now regularizer term that says that your true inverse model Q should not be far away from the tau. So, whereas previously you did not have any restrictions on Q, now you do. You need Q to be simple. So, how much did you gain? It's not clear. Probably this bound is better than the original elbow because your Q can be more expressive, more flexible. But then it is still not as good as we would probably get if we had access to the density itself, because there is this regularizing term. You can't have arbitrary complicated Qs. So this is something to deal with, at least for now. Yeah, this is something that has to be said. And another problem to be wary of is that, so this is not just, in this case, Q is not just a hierarchical model, but it's a conditional hierarchical model. That means that if your Q for some reason decides to zero out all the connections to psi that it has, it will still be able to generate some non-constant output due to this conditional input of x. So in the worst case, it can degenerate back to a standard tractable distribution like Gaussian distribution by just ignoring the psi, the inputs psi that it's getting, by zeroing out the corresponding weights. This is something we would not want. We would like to prevent. But for now, let's step back a little and go into a different direction. So there is another way to tighten the lower bound, to get a tighter lower bound on the marginal likelihood, and that is of using multiple samples, and in particular the importance weighting autoencoder's lower bound. It has the following form, where you basically take a batch of m samples from your Q, all independent and identically distributed, and compute the estimate of marginal likelihood, not log likelihood, and then take the log. So it can be fairly easily shown that this is a tighter bound. It is an upper bound on elbow and a lower bound on the marginal log likelihood. And it's known as importance weighted variational inference. It can be shown to essentially correspond to some kind of a refining procedure that takes in your Q, your simple Q, and sort of augments it with the non-parametric procedure on top that is meant to improve your samples. The procedure looks like this. First, you sample m independent identically distributed random variables from Q. Then for each Q, you compute its elbow. Then you would like to select, then you choose one of those samples, and you choose each sample with probability that is proportional to its elbow. So the higher the elbow, the more likely you are to select the corresponding sample. And then you just return this sample, say that here it is, it's the best sample that I could find out of these capital M samples. In a sense, so what does it mean to have big elbow? Well, the elbow will be big when you have the sample from the approximate posterior that falls in the region where the true posterior has high probability and the approximate posterior has low probability. So it sort of adds exploration in the right place for your model.
Tom, I still do not see the connection between this procedure and the IWL1. You mentioned that it can be interpreted as a refining procedure. The refining procedure is as follows, but I still do not see how it can be interpreted.
Yeah, and now I'm about to answer your question. So the problem is that, okay, we could envision such distribution Q hat, such refined distribution. However, actually its density is intractable, so we can't compute the elbow for such refined distribution. However, it turns out that the IY elbow, the IY bound, is a lower bound on this intractable elbow that sits right in between the elbow of your Bayes distribution Q and the elbow of that refined distribution Q. And the IY elbow is tractable one.
Well, but you need to show at least that the right-hand part is larger than standard elbow, right? And then you also need to show that IY lies in between.
Okay, this is not my result, so I won't be showing anything. It has been already shown, and there are citations for people who are interested. I'm just familiarizing you with the background. So all that was meant to say that having multiple samples is another way to actually consider a more complicated model, kind of a hierarchical one, and then also give a lower bound. The downside of this bound, though, is that it requires you, for each of the M samples, of the capital M samples, you need to evaluate the joint density, and if your X is high dimensional, as it usually is, then those evaluations might be very costly. So now the question is, okay, we can use multiple samples to tighten the lower bound. Can we do the same with the upper bound? That would be neat, right? Well, the answer is sure. We have an unbiased estimate of something. Then let's just take, so if we have capital M equal to 1, then this is exactly the derivation I had for the hierarchical variational models bound. Now we just take a Monte Carlo average under the expectation, where the expectation is again over M IID size. And then by some essentially equivalent algebra, we arrive at the following estimate, at the following upper bound. Does that make sense?
Yeah.
But now the question is this bound even practical? And the answer is, doesn't seem so. So the biggest trouble here is that we need not only one sample from the true posterior now, but a capital M of them. And even we have one sample from the true posterior for free, but only one. We can't have more. In order to generate more samples, we would need to go for Markov chain Monte Carlo. And moreover, in practice, this estimator is known as the harmonic estimator, and it is criticized to be a very poor estimator. We won't be diving into details as to why it is very poor, probably due to the need for the Markov chain Monte Carlo samples. So forget about all this. We can't obtain multisample variational upper bounds this way. However, last year there was an interesting paper called Semi-Implicit Variational Inference, which said that, well, that wasn't claimed in the original paper, it was shown later by our people. But so the core result is that actually this thing, this term, this guy, is a lower bound on the elbow for hierarchical Q, and thus a lower bound on the marginal log likelihood. If you massage the formula even further, you can sort of arrive at the following upper bound on the marginal log density. I am not sure if you can arrive at this formula from all the statements in the CV or DCV paper, but that doesn't really matter, it still holds. So this is a very interesting lower upper bound on the marginal log density, and let us recall a lower bound.
We generate the psi 0 from in some sense posterior from the conditional distribution conditioned by Z, and we generate all remaining psi's from some kind of prior.
Yeah, exactly.
Which we can do easily.
Yeah, and then we can also easily evaluate the conditional the conditional densities. So the whole thing is very tractable, and you can compute it as long as k is not too big, of course. Now let's, for a second, recall the lower bound, the IY lower bound, the multisample lower bound. It looks like this, and moreover, let's consider a special case where our variational distributions for the importance weighted bound is equal to the same prior, to Q of psi, not conditioned on Z. Then we get the following lower bound. And if you look closely, these two terms look suspiciously similar. The only difference between the two is whether or not the sample from the true posterior is included. You take a lower bound, you add a sample from the true posterior, well, of course you also add one here, and suddenly the bound becomes an upper bound. So at this time I questioned myself, can we so consider now this thing, essentially a lower bound, the IY-like lower bound, where we also throw in one true posterior sample. Can we show that this is an upper bound? We already know that this is indeed an upper bound on marginal log density for the case where tau is equal to the prior. Moreover, upon careful investigation, we can show that if we put capital K equal to 0, then we will recover the hierarchical variational models bound, this one. Of course, if you use instead of tau the true posterior, the true inverse model on distribution of psi conditioned on Z, then we will exactly recover the log marginal density. I think this is a typo. This should be Z conditioned on X and only X. So after some time of doing random mathematical stuff, I came up with the following theorem that shows that basically yes, this is always a lower bound, provided some regularity conditions are satisfied. Particular, but they're nothing fancy. We just ask that our tau is a flexible, is a reasonable approximation for the psi given Z. That is, their supports relate in a meaningful way. Now we denote our upper bound by U with subscript K, and we can show the same statements as were shown for the IY bound. namely that is always an upper bound, that it gets tighter as you increase the k, and in the limit of infinite k you recover the marginal density exactly. I won't be proving all of this. I will only show you how to prove the first statement, that it is always an upper bound. So consider the gap. If what we have is indeed an upper bound, then the gap between our bound and what it's supposed to be bounding should be always not negative. Let's show it. So first we consider this difference. Now we can move on since this thing is a constant with respect to psi, we can move it into this thing all the way to here. So essentially we will divide our joint density by the marginal density of z. This is exactly the inverse model, the density of psi given z. Okay? And now we do, we divide and multiply by the product of the densities we are sampling from. Basically to get this thing. Here's another fraction line. Does that make sense? And then if you look closely, you can say, wait, this looks familiar. This is basically a KL divergence. And KL divergence is always non-negative, so we're done, right? But you can ask me, like, wait a second.
The second argument is distribution.
Yeah, is it even a distribution, right? Yeah, indeed it is, so let's show it. So we would like to show that omega defined by this fancy formula is a distribution. That is, it integrates to 1. I mean, also we would need to show that it is always non-negative, but this is obvious because all the terms are non-negative.
Right.
So let's do actually some integration. First we multiply and divide by tau of the 0th psi. And then we know that this thing, the resulting expression, is sort of the choice of 0 is arbitrary here. We can consider a change of variables where we exchange psi 0 with some psi j, and the only thing that would change is that here we would need to write j instead of 0, and everything else would not change because it is already symmetric under any permutations of z. So that last term is equal to this first term. Now, since this is true, since this is the same expression, the same value, the same integral for all choices of j, then let's just average over all of them. It will be the same value. So we obtain this thing, and then we move the averaging inside. The only thing that depends on the averaging is only this term. So we get expression looking like this, and now we can see that there should be like brackets here. The numerator and the first term in the denominator and the first term in the denominator cancel out, leaving us only with the joint density of all psi's, which does integrate to 1 because it's just the density of a random variable.
Sorry, can you explain once more how did you replace the 0 with j?
Yeah, so consider a change of variables. You have some original vector of psi's and some transformed vector of psi hat. So in psi hat is the same as psi, except you flip over jth and zeroth components. So that means that psi hat j is equal to psi 0 and psi hat 0 is equal to psi j. Then after you done such a transformation, the Jacobian would be 1, so there would be no additional terms here. Here you don't need to rearrange this density because it is already invariant to any permutation of psi's. And as well, and the same applies for the denominator. You don't need to do any changes to the denominator. It is also already invariant to any permutations. So the only thing that changes is actually here. You would need to replace 0 here with the j. So yeah, and the rest is just simple averaging.
Wait a second, doesn't it mean that omega is actually equal to tau? Oh no.
No, it does not. It
Well,
only means
very-
so where k is equal to 0. I think so. No, it's never so. I guess for k equal to 0, it is equal to the true posterior.
Does it break when
Or
we
maybe
move
tau.
from like the second row from the bottom, from the left part to the right part? Does it break here?
Here?
Yeah.
What exactly?
So we only did some like juggling with the probabilities in omega and did not use the integration sign anywhere. And then
What sign?
the integral sign, the integral.
Well, we use the integral here.
Yeah, but didn't we just use that the sub-integral expressions are equal? This.
Well, but if integrals are equal, it does not mean that the thing you integrate over are equal.
It seems like they do it the other way around. But yeah, I guess it breaks on that sign. So we only use the integrals are equal there. Under change, under the word change.
Yeah.
Okay.
Yeah, I guess it's also maybe happening here because you use this this invariance under any permutation, and this is also a very important property of this of the whole thing.
Yeah, I see.
And that concludes our proof. Since this is a distribution, then on the previous slide we did indeed have the gap between the bound and the marginal log density equal to KL divergence between two valid distributions, and it thus follows that this gap is non-negative. Let us see how this upper bound compares with previous methods. So we already know that we can get an upper bound from HVM and from CV. Both are actually special cases of upper bound, which is neat. And we will consider this d-dimensional Laplace distribution, which can be shown to be a hierarchical model, namely the so-called scale mixture of normals distribution. So essentially, you sample. You have a normal distribution on Z where the variance comes from the exponential distribution. Then turns out that marginally such Z's are distributed as Laplace distribution. So in order to, we will be considering upper bound on negative differential entropy, since we actually need to average our samples from Z. And as a proposal, so actually for such model, it is known that the true posterior has the so-called generalized inverse Gaussian distribution, Unfortunately, it is so obscure that not only you haven't heard about it, but also it is not implemented in any packages. And then we actually, to test our bound, we're not interested in cases where we can approximate the true posterior exactly. Then there would be no benefit from our from using multiple samples. But we will be using gamma distribution, and gamma distribution is a special case of this generalized inverse Gaussian distribution. So this is the bound we'll be considering. Essentially, I just used the bound I presented to you on the previous, some of the previous slides, and substituted the specific distributions here. So gamma here, parameterized by alpha and beta, is our tau, our auxiliary variational distribution, and alpha and beta are neural networks that you take in z and output those the parameters of the approximate distribution tau. Also, in this, since we have since tau is variational and we can choose any tau we want, we use our freedom to design this distribution and initialize it in such a way that at first these networks alpha and beta output values that are close to 1 and 1/2, and for such choice of values the gamma distribution approximates the exponential distribution with parameter 1/2.
Approximates or exactly equals to?
Well, for if alpha and beta were exactly equal to 1 and 1/2, then yeah, it would be exactly equal to the exponential distribution. So this way we are guaranteed to initialize at well, almost at the CV bound and improve upon it if possible. And indeed, the plot shows that it is possible. So I think you should be able to see this dashed line that corresponds to CV. Then if we make only 10 optimization steps, then we would not be able to go far away from the initialization. It's not enough to warm up our network, our neural networks alpha and beta. But if we make at least 50 steps, then we are somewhat better. The more steps we make, then the smaller the gap is between the true value, this horizontal line, and our approximation. Moreover, you can see that as you increase k, first the bound drops rapidly. Like here, this point is probably corresponds to k equal to 10. So we can see that taking just 10 samples improves your bound significantly. Maybe, well, almost as if you, almost gives you the same gain as you got from training your proposal. The other thing to notice is that although CV uses samples from the prior and is indeed the worst performing method on this plot, well, especially since I designed the whole experiment so that I can be no worse than the CV, but still it is interesting to see that. So here for the k equal to 0, we have values for the HVM bound, and those are continued along the way along these horizontal lines. So CV actually beats all the HVM bounds, no matter how well you train them. But you can take just 10 samples for the sort of HVM, that is for the IVHVI, and you are already much better than the CV. In the end, you can arrive at much better estimates of the log density than the CV does. And it's not looking like CV is making much of a progress in that area. So in order to match the IVHVI's performance, CV would probably need a lot more samples.
So that's quite important result. So we can conclude that both things are important. We need better and more flexible variational families, which in this case correspond to HVM. And at the same time, we need to make use of case sample estimates. So the larger case we use, the better we approximate the two posteriors. So both terms are important. And in this IWHVI model, both terms are integrated. So in a sense, this is generalization of two existing techniques, CV and hierarchical variational models.
Right. So I guess you can think of the IVHVI as the. So if you remember, when we talked about the IVI, we said that it can be seen as this refinement technique that improves your posterior, your proposal. You take some simple proposal, you run through this sample and selecting procedure, and you get a better proposal, though somewhat implicit. Essentially, the same happens here. The more samples you use, the more computation you use, the better your refined proposal is. So this improved variational upper bound on marginal log density allows us to come up with a better sandwich bounds for KL divergence. Previously, well, assume that you have two distributions Q and P, and both of them are hierarchical distributions in probably different spaces. Like zeta and psi might live in totally different spaces. Then you can come up with the following upper bound. So essentially, this guy estimates QZ, and the denominator estimates PZ. You can see that for this KL divergence, you would have log Q with a plus sign and minus log P. So in order to give an upper bound for KL divergence, you would need to estimate log Q from above, to bound it from above, which you do using the IVHVI bound, and bound the minus log P from above, which is equivalent to bounding log P from below, which you do using the standard importance weighted bound. You can reverse the whole, and here we already used the fact that we don't need to explicitly sample from the inverse model of Q. We can just sample Z and psi jointly. Now you can combine the same facts and derive a lower bound. So you estimate Q from below using the importance weighted bound, and P from minus P from below, that is P log P from above, using the IVHVI bound to arrive at the following expression, an obvious one, except this time you actually need to sample zeta 0 from the true posterior, and at least for now, I don't know any ways to get rid of this posterior sampling. So this lower bound is not as tractable as the upper one. In upper one, we used this trick of free posterior sample, whereas in the lower one, no such trick is available. Luckily, we are rarely interested in lower bounds on such hierarchical distributions. So I won't be having, and I didn't have any experiments with such bound. I only listed it for completeness. Also, I didn't perform any experiments with the hierarchical prior P, because this is roughly corresponds to having doing kind of nested variational inference, and there are papers on that. The focus of my paper was about hierarchical proposal Q. So yeah, this in these two formulas, obviously tau and nu are auxiliary variational distributions, just variational distributions that are meant to approximate the inverse true posterior of Q and the true posterior of P correspondingly. It also should be probably noticed that although I use the same letter tau and tau here, actually since those are the bounds, the gaps between the bound and the KL divergence are different in both cases. So the gap between this bound and the gap between this bound are not equal. So when you optimize over tau, you minimize in different gaps. So if you actually want to estimate both upper and lower bounds, then you probably should be using different taus and different nus for upper and lower bounds. Does that make sense?
Yeah.
Okay.
It would be very strange if it appeared that you should use the same tau and u.
And yet that would be very nice. So yeah, now you just plug this Kyle estimator into an elbow. Again, I assume that we have the prior density available in closed form explicitly, because I'm not that interested in the case of hierarchical prior, and arrive at the following lower bound for the hierarchical multisample hierarchical lower bound. I call this the importance weighted hierarchical variational inference bound, or short for the important VHVI. Now, obviously, for some special cases, you obtain previously known methods that how the bound was actually sort of designed. For the choice of prior on psi, you get the semi-implicit VI bound. For k equal to 0, you get the HVM bound. As a special case of the HVM bound, if your if your prior actually is hierarchical, then and operates in the same space on the same size as Q, then you can consider this weird case where your true posterior for the variational posterior for Q is equal to the true posterior for P, something which looks quite ridiculous, and then by rearranging the terms, you get the whole joint in the denominator and the proposal joint in the denominator, and that corresponds to just plain joint variational inference, where when you consider both the sort of concatenated pair of z and psi as a latent variable. That's the way people at least tended to do, I would say, variational inference in such hierarchical models some time ago, and it's based on very unrealistic approximations, I would say. This thing is very unrealistic, so I would advise you not to use this bound.
Why is it unrealistic?
Because as a variational distribution for Q, you use the true posterior for P, and generally speaking, these two are very, very different.
Well, in the DC paper, we tries to perform inference with such joint bound, and the inference is absolutely the same model, but the CV bound, and well, the CV bound smashes the joint bound.
Meshes?
Smashes.
Smashes.
So, how do we compare in more qualitative terms with such prior bounds? Well, one benefit of the semi-implicit VI is in its name, that it allows for semi-implicit variational distributions. Namely, for cases where you distribution Q of psi is implicit, that where you don't know the density. If you recall the bound, the CV bound, you don't actually need to know the prior density here anywhere. You can have fully implicit model as your prior, and just sort of smoothing it using the prior, this likelihood, this z given psi. So whereas the IVHVI does require you to need the prior density of psi, and at first sight that might be limiting and even troubling, but I would argue that you can, since anyways we assume that the psi given x is reparameterizable, we can move the randomness into this independent parameter epsilon that comes from the reparameterization and consider an equivalent model. So if you have this model with implicit but reparameterizable Q of psi given x, then you can say that psi is actually a random variable that is obtained from epsilon. So why don't we consider an equivalent model where we bake this reparameterizing transformation into our likelihood z given psi, and only put into this likelihood, only feed this likelihood with epsilons, and epsilons would be coming from some standard distribution like standard normal or wherever else you use for the reparameterization trick. So in most cases that is not a limiting factor. So therefore in the following and in all the talk I have assumed, without much of a limitation on the generality, that we know psi's density. If we don't, we can consider an equivalent reformulized model, reformulated. Another thing is that since we since we have additional, yeah.
I have a question about the first thing. Did you try to compare, for the same model where you can compute the density of psi directly, try to write it down as this model on the right with epsilon, would the IVHVI bound be better when you access the density of psi directly rather than using the epsilon? I would think that in some cases this may be crucial.
Good point.
So I think at least it is something that
I am not sure, because the two are related by the deterministic transformation, and the one density. So the density of psi is actually the density of epsilon times the Jacobian of the reparameterizing transformation. So if you can compute it, well, good for you, but doesn't look like it's buying you much. And then you would need to do variational inference. You would need to approximate tau in a more complicated space, where not only your posterior is super weird, but now also the prior is also weird to start with. So that probably means your posterior that you're trying to approximate. I don't think that the posterior should change in any way.
But at least, if you move to epsilons, you disregard the conditioning, so that your tau would be not conditioned on x, for example, and thus probably less flexible.
I am not sure you can. I'm not sure you can get rid of the condition on x. We can discuss it later, but in my attempts, I think you cannot get rid of x in tau.
I would assume that since we're dealing with semi-implicit distributions, our approximation schemes should be dependent on the decomposition between z and psi. So if you use different decompositions, if you use different psi's, I would assume that your variational approximation schemes will be different. And there's dependence on the choice of this decomposition. I think we need to explore it in details, at least in theory.
Yeah, sure. So since we have an extra model tau here, we also need an extra run through the neural network that parameterizes the tau. We need to somehow get parameters of the tau. How do we get it? Well, we run the z and x through tau's network to generate these parameters. That's an extra computation that you didn't need in the CV. That is something to consider. However, I would argue that you only need to do this once for every sample z, and after that you would need to evaluate the density. Well, essentially the joint density of such sample k times. So this computation, the computation of z given psi, is likely to dominate the one bit of computation, the one run through a new network to generate tau. Does that make sense? So essentially, you do k passes through this network to generate psi's, and only one pass through the network to generate the proposal for psi's. So one extra run through a network does not really change much, especially since for CV usually requires much larger k to achieve the same quality. So probably that should be said somewhat earlier, but we have already observed that the CV bound is a poor one. Why is that the case? Well, there is math that says that we can optimize the IBHVI, and if we can do better than CV, we will. But the intuition is that in the CV you use, let's take a look at this formula. Here you use samples from the prior to describe a given z, and only one sample is coming from the distribution, from the true posterior. So only one sample actually is related to z in any way. All other samples are just educated guesses. You don't. All these samples have no idea what this z was. They are uninformed. They don't know where to look for the z. So this was one of the motivations for this work. Why we did empirically observe that the CV bound is poor in its approximation quality, and this is essentially due to it's making a kind of a random search. It just tries a bunch of things and sees whether they describe the marginal, where they describe z well. That's what this point was saying about. And HVM lacks the multisample tightening, essentially using just simple Q as a proposal, whereas IBHVI uses this refined proposal. In practice, to evaluate variational autoencoders, people use importance-weighted bound with a ridiculously large m, like 5,000. Well, maybe it's not that large, but whatever. So it would be nice if we could combine our bound with IVIA, so that we can also use it maybe during training to further improve our Q in this sort of double refinement way. Or during evaluation, so that we not only refine Q but also improve our tau, so that we don't suffer from this auxiliary approximation. Question? Okay. So yeah, indeed, you can show that very similar to the IVI, you can take m independent samples of everything except z, except x, sorry, and write down the full formula, and it will be a tighter lower bound, sort of doubly importance weighted hierarchical variational inference. Although maybe I should have come up with a better name because it's only once hierarchical but doubly importance weighted. So yeah, one of the hardest names.
Importance weighted, monthly, hierarchical.
Yeah, so you know, naming is one of the hardest things in computer science. Now, this bound is much more computationally demanding, as it requires you to take m times k plus 1 samples of psi from either from prior or from the tau. So that's not nice. Interestingly, in the CV, one could do a neat trick. And since all the samples are uninformed either way, they are not tailored for any particular z, then we can reuse them. Basically, we can generate m samples of z from the corresponding psi's, then we can generate extra k samples psi, and use all the samples psi we got to estimate the marginal log density. That would still be a valid lower bound, although, to the best of my knowledge, not explored in any published paper to the moment. That's still a valid upper bound. It's interesting because it only takes a linear number of samples as opposed to quadratic in our case, but does not allow. So, unfortunately, this trick cannot be combined with the IVHVI bound, the d-IVHVI bound. The reason for that is that, remember, when we derived the IVHVI upper bound, we heavily relied on the symmetry. And this symmetry manifests itself in that for given m, the small m, the nominator should be symmetric under any permutation of its terms. So if some of psi's were conditioned on different z, then that would not be a lower bound anymore. And if some of psi's were coming from different distribution, not tau and not the true posterior, that would also not be a lower bound. So, long thing short, we cannot use the same trick in the DIVHVA. However, one could consider a multisample conditioned proposal, a tau that is conditioned not on single z but on all of them in a permutation invariant way, kind of as a set level operations. Then I think it should still be a lower bound, although we did not explore this direction in the paper, and maybe this is a possible line of future work.
Yeah, but then you would have to use the same amount of m during training and testing, which is not ideal.
It depends on your network. I think you can, like there are transformers, for example, are example of set level neural networks, and they can work with variable length inputs. So hypothetically, you could learn a model that works with different number of inputs.
Mm-hmm.
Maybe even learnable number of inputs. You know, have some prior. So for the VAE experiment, we used the DIVHVI bound with m equal to 1 during the training and gradually increasing from 1 to 50 over 10,000 epochs. And for testing, we used a kind of standard approach of 5,000 IVI samples and 100 IVHVI samples. We used only 100 because first it was already computationally demanding, and second, although I don't have any plots to show you, we observed near saturation around for case of like 10 and 50. So I don't think much would change if I used k equal to 200, for example. Since CV lacks tau and we would like a fair comparison, we actually trained, first we trained CV using the prior tau, and then for the fixed model we learned only tau for, we made some 7,000 epochs learning on the tau, and yeah, use that tau in the, during the evaluation stage. Those are some details on our architecture, and the architectures were fairly standard. The results are like this. So the AVB plus AC stands for adversarial variational bias with adaptive contrast, and those are numbers from the paper that presented this method. It is actually a method that is based on the density ratio estimation kind of approach. So they did not optimize the lower bound during training. Instead, some approximation to it. And all the rest methods are bounding methods, or these two are the flows. So these two are more theoretically sound. And especially these three are different cases of our method.
And so BayesGroup was estimated using IVA?
Yeah, using this setup. So although we didn't beat the AVB plus AC, that wasn't the goal. The goal was to show that we are better than CV, and we are, so hooray.
Did you use the same way to evaluate HVM, or did you use just standard HVM bounds?
I used standard HVM bounds. Moreover, HVM actually collapsed to the VAE. Its tau was equal to the prior, which means that the Q did not use psi at all. This is another interesting direction to investigate our bound that we won't be diving into more specifically, but I would only briefly mention it, that having this more expressive Q is somewhat equivalent to relaxing this regularization. Recall that when you optimize the bound instead of the quantity of interest, you are not only maximizing the quantity of interest, but also minimizing the gap. And the gap acts as a regularizer. In the VAE, it prevents you from learning two expressive generative models. Your true posterior of your VAE has to be not that complicated, not that far away from the variational proposal. When you use IVI like refining, you're essentially this gap is reduced, and the gap is now much more forgiving for the true posterior. It does not need to approximate the marginal, does not need to be close to that close to the variational distribution, but can be much further away. So this is actually one of the reasons why such improved inference translates in better scores on the evaluation of the generative model. We managed to learn better generative model because our Q was more flexible and much less restricting than CV.
I also have one more question.
Yeah.
How does one evaluate the test of likelihood on the models like AVB, where the elbow computation is biased?
Yeah, in that paper, after we used annealed importance sampling, I tried to use it as well, but couldn't make it run. Also, there is a paper that says that annealed importance sampling is a much better way to estimate marginal log densities than IVI is. All my attempts to get even close answers to those of IVI failed. So I'm not actually sure how much trust we should put into those numbers.
Yeah, yeah.
And the standard deviation was reported by the authors of AVP.
Yeah, and minor 2 standard deviation interval. Now, so this is actually, so for now the main part is mostly over. I'll just briefly mention some of the extensions. So since our paper is, since our method is so similar to the IY, we should thought maybe some of the, and people have been studying IY for quite some time, maybe some of the results can be carried over and applied to our bound as well. In particular, one of the main concerns was that for the IY bound last year, it was shown that the paper called Tighter Bounds Are Not Necessarily Better showed that when you increase the m number of samples in the IY, the quality of your gradients can actually degrade, and it can complicate the learning. In particular, if you consider if you consider gradients with respect to theta in the IY model, then everything is good for them. The bigger m you take, the more samples you use, the better the gradient estimator behaves. It has increasing signal-to-noise ratio, meaning that there is less noise in your gradients and more signal, leading to better stochastic optimization. Stochastic optimization is sensitive to the variance of your gradients. But unfortunately, in the same setting, if you take a look at the gradients with respect to variational distribution Q, then they are degrading as m increases. As m increases, the signal-to-noise ratio of these gradients actually goes down, and this is troubling. But luckily, we were afraid that maybe the same problem exists in our model that would sort of undermine our efforts at using multiple samples during training. Well, they do, since using multiple samples during training is favorable because you can learn more expressive posterior distributions. They are less restricting on the model you're actually trying to learn. But if you have hard time actually learning them, well, maybe you then are better off with the prior, that is the CV method, which does not need to be learned. Luckily, by the end of the last year, it was shown that the source of this decreasing signal-to-noise ratio problem is actually a hiding reinforced-like term in the gradient estimator. That is right, you have a reparameterized gradient, and suddenly inside of it somewhere there is a reinforced-like term hiding away from you and messing up with your variance. However, once you identified it, you can apply the reparameterization trick the second time and get rid of it. So there was a paper cited here that showed that by doing such by using such doubly reparameterized gradient, they actually solved the decreasing signal-to-noise ratio and basically solved the whole problem. So long story short, everything applies exactly the same thing applies to our bound. Well, almost exactly the same. We also suffer from the decreasing signal-to-noise ratio, and again, they can be a reinforced-like term can be found in our bound. It can be successfully eliminated, eliminated using the reparameterization trick applied the second time. And here are some of our empirical study. Here's some of our empirical study. So here we have, first I would like to show you the problem for the IY bound. We are, so for the IY, if you use just standard gradients that are provided for you by automatic differentiation, the magenta line, I guess, then indeed the signal-to-noise ratio decreases as you increase number of samples that you use to estimate the bound. However, if you use the so-called doubly reparameterized gradient, the shorthand drag, then the green line is actually much better, and the variance improves as k grows. So it solves the vanishing, the signal-to-noise ratio problem for the IVI. Now, if we take a look at our gradient estimates, then the naive gradients are the purple one, and they exhibit well, almost the same behavior as the IVI ones, with decrease in SNR over increase in K. Now, if we do the same doubly reparameterization trick, then unfortunately we won't be getting increased SNR as in IVI case, but instead constant SNR. That was, and the reason for that is that, remember, we have one sample from the true posterior. From this term comes almost a reinforced-like term, but not exactly, so we can't apply the reparameterization to it, and that one messes with the gradients. If we omit this term, the sample from the true posterior, then, well, of course everything will be good as is shown here in the orange line, because we would essentially recover something like a IVI bound. But still, this solves the vanishing SNR problem. Another possible improvement is combination of the IVI with the jackknife estimator. In statistics, it is known that if you, so since IVI can be seen as a biased estimator of marginal log density, log likelihood, we can say that the following holds when there is an equality sign here, that the marginal log density can be, oh no, this is just the difference, so the gap between log density and the IVI bound can be seen to the first order. It has behavior like some constant over m number of samples. And so you can apply this so-called jackknife estimator to reduce the bias from 1 over m to 1 over m squared, then repeat the same procedure over and over again and reduce the bias to 1 over m to the power of d plus 1 for d times repeated jackknife estimator. The problem though is that such improved estimate, the biased estimator, is not guaranteed to be a lower bound anymore. So it's more of an approximate estimator category. And again, the same can be applied in our case. Here are some plots to show that indeed it gets better. Interestingly, here it always was an upper bound. However, as you get closer, that is likely to not be true anymore. And that's it. So let us recall what has happened in the last 90 minutes. So I presented a tighter variational lower bound on the marginal likelihood. I showed that it generalizes many previously known cases like HVM, CV, and the joint bound. We saw that it does improve upon special cases, both on toy tasks and on more, somewhat more challenging ones. It can be combined with many, it is very similar to IVI and can be combined with many results that were applied to it previously, that were developed for the IVI previously. And I think there is still some some things unclear about this estimator. In particular, it's not obvious why omega is a distribution, what it actually is, why we essentially have an unbiased estimator of 1 over the density, and the relations to IY can be elaborated more clearly, I guess. Here's the slide with citations if you're interested in learning more, and thank you. Do you have any questions?
I think that most of the questions have been already answered. Yeah.
Excellent. So I would not hold you anymore from the wonderful evening of Friday. Thank you all for attending and see you next week.